Hello and welcome once again to Physics for the 21st Century. My name is Greg Perugini and today's topic is linear momentum and impulse. So first we have to define these terms and what linear momentum is. And linear momentum is a way that we can describe and model a particle in terms of its movement with velocity. Linear momentum, we use P equal mv. Its mass is a scalar, momentum is a vector, and of course velocity is a vector. So know that momentum is conserved. In a closed system, the momentum final must equal the momentum initial. And what we call impulse, we're going to use an I for that, is a change in momentum. Momentum final minus momentum initial. So, impulse would be the difference between these two in a system where it is not conserved. Let me give you an example. If I am hitting a ball with a tennis racket, I'm implying a force in changing the momentum of that ball. So we can also write this impulse in something called the impulse momentum theorem. Impulse is equal to the change in momentum, which is also equal to force for a given period of time. Now, for a given force, there would be less impulse if the time was greater, if you look at that equation. So sometimes it's easier to just show you in an example here. Let's first do a problem in terms of linear momentum. I have two people. And they're on ice with ice skates, and they press off of each other. It's person one and this is person two. And this person is 75 kilograms. And this is 100 kilograms. And after pressing off, we can measure that this person is going 3 meters per second. What is the velocity of the first person? Well, we can use momentum to solve that, providing that this is a closed and isolated system, nothing is going in and out. The momentum before must equal the momentum after. Well, before, for both velocities, they're at rest. Nothing's moving. So there is no momentum in the system before. After, for number one, P equal mv, the mass 75 kilograms. The velocity, we don't know yet. For the number two, we have the mass and we have the velocity. So we know the momentum of number two, 300. Momentum, of course, if you can look at that, you can easily see momentum's units is kilogram meters per second. So this plus this, 1 plus 2, better equal what? 0. Momentum before must equal the momentum after. So you see here, we can write this down, 75 velocity 1 is equal to, or I should say plus, we're adding here, plus velocity velocity of 2 times its mass, which comes to 300, equals 0. Well, doing the math, very simple algebra, we get 4 meters per second. Now, that's fairly straightforward, right? And you see these, when we talk about collisions in another topic, you're going to get a little bit more complex of a type of problem there. But this is fairly straightforward, right? In one dimension, momentum before must equal momentum after. Let's look at impulse. Now, on impulse, let's say we have a ball coming down. This is in the x and y coordinates. And I have a ball coming down. And that ball is traveling at -3 meters per second. It's coming down. It is a 2-kilogram ball. And it hits the ground and bounces up. Bounces up at 2 meters per second. So clearly, momentum isn't conserved here, right? Something is lost, and we're going to look at what's lost here, because if we write down the momentum, the impulse momentum theorem, momentum final minus momentum initial is equal to impulse, which is the force for a given area or for a given time, change in time. The momentum final for this ball is mv 2 times 2. The momentum initial is 2 times -3. What's that lead us with? 4 plus 6, negative and a negative, 10 Newton seconds. Newtons second, the units, Newtons seconds. The units for impulse. So that's the impulse. But with this equation, I can also calculate force if given time, or time if given a force, because let's just add to this. What is the force? If contact is for, let's say, 0.01 seconds, 100th of a second. Well, for this, we need to use this part of the equation. Okay? That part of the equation, right here, we know the impulse is 10. We know the force can be solved if we have the time, 0.01. So the force imparted is 1,000 newtons. So this impulse momentum theorem, particularly in one dimension, again, we're going to be covering this more in 2 dimensions, in another topic of collisions coming up soon. So as I said, we can model this, model movement for a mass as momentum, and the change in momentum being impulse. So if I'm swinging a racket, obviously, as I said, or swinging a baseball, swinging a bat at a baseball, I want to follow through so I have a greater amount of time on that particular object, whether it be a tennis ball as you see here, or whether it be a baseball or whatever. And that would allow for a greater amount of force to impart. The impulse would be greater. So, in conclusion, remember, momentum is conserved, and the before must equal the after. Know the impulse momentum theorem, and do some examples in the book and online, and everything should work out for you. Good luck.